All right, my friends, let's take a look at the idea of a function. So suppose we have a function that adds 3. So what that means is you have something that you accepts an input, and then the function just adds 3 to it. So the function that adds 3 might be written something like this. F of x equals x plus 3. So no matter what x value you give it, you just add 3 to it, and then that's the output. So for example, if we look at f of 2, if we give this thing an input of 2, and we give 2 to the function that adds 3, well, the function will just add 3 to it. So 2 plus 3 is 5, and you get an output of 5. So whatever you give the function f, it just adds 3 to it. So let's mess with this a little bit more. Suppose we have f of 2. This means we apply the adding 3 function twice. Well, the first time we apply the adding 3 function, we're going to get 5 because 2 plus 3 is 5. And now we have to apply the adding 3 function one more time. So f of 5 would be 5 plus 3, or that'll get us up to 8. And notice the net result is we have added 3 twice to the 2. And so 2 plus 3 actually gets you up to 8. Well, let's look at another case of this. We've got f of x. Well, we apply the adding 3 operation twice, so we have to add 3 and then add 3 again. So the first time we add 3 to x, we're going to get x plus 3. And the second time we add 3, we will get x plus 6. So x plus 3 would give you x plus 6. We can think of another function, something that quadruples. So this would take anything you give it and multiply it by 4. So the function that quadruples we might write as g of x equals 4x. So whatever the x is, you just multiply it by 4. So for instance, g of 2. If you give it an input of 2, you just have to quadruple the 2 and get as an output an 8. Let's try a few of these, messing around with this new function. Suppose we had f of g of 10. When you see something like this, you kind of work inside out. The g function will act first. So the quadrupling function will act, and then f, the adding 3 function, will act after that. So we're going to quadruple, and then we're going to add 3. So let's try this with the 10. If you quadruple 10, you'll get 40. So we've now sort of used up the g function, and now we just have the f function that adds 3. Well, adding 3 to 40 will give you 43. Another case might look something like this. Just reverse the order. G of f of 10. Well, you got to work inside out. We're going to apply the f function first, so we're going to add 3 first, and then we're going to quadruple by applying the g function last. So again, you work inside out. Well, so f of 10, we just have to add 3 to the 10 to get 13. And then we have to quadruple the 13, which ends up giving you, well, 52, since 13 times 4 will give you a 52. A couple more examples. Let's try f of g of x. Again, working inside out, we would apply g first, or quadruple first, and then we would add 3. Well, so if you quadruple the input of x, you get 4x. And if you add 3 to 4x, you get 4x plus 3. Another case might look something like this, just switching the order, g of f of x. Now we're going to add 3, then quadruple, because the function fx first. So add 3, then quadruple. Well, if you add 3 to x, you get x plus 3. And if we quadruple that whole thing, you'll get 4 times the entirety of x plus 3. And just to make it pretty, you can distribute the 4 to get 4x plus 12. And then very last example here, we'll step it up a notch. Let's do f of g of f of something called b. Well, so again, you work inside out. So the first thing we have to do is take whatever b is, and then f is the function that adds 3. So we're going to add 3, then we're going to quadruple, then we're going to add 3 again because of this outer f that's acting. So it's going to look like this. Add 3, then quadruple, then add 3 again. Well, so if we add 3 to b, you get b plus 3. Now we have to quadruple b plus 3. So we're going to get 4b plus 12 by quadrupling b plus 3. And then the very last thing we have to do is add 3 to that whole mess. So you'd get 4b plus 12 plus 3, and then of course you can combine the 12 and the 3 to make a 15. All right, now let's look at how we determine whether something is a function or might not be a function. A key property of functions is that they have only one output per input that you give the function. So for example, let's look at a case when something could be a function. here in this case, if you put in a 2, you get an output of 1. If you put in a 3, you get an output of 3. Put in a 4, you get an output of 5. Put in a 5, you happen to get 5 again as an output. Well, if you plot these inputs and outputs, so here are these 4 points using the inputs as the x-coordinate and the outputs as the y-coordinate. You see that for every one input you give it an input of 2, bang, you get that output of 1. Give it a 3, get a 3, give it a 4, get a 5, give it a 5, you happen to get the same output, but that's all right. That's a function. You have one output for every input. Let's look at a case when you have something that's not a function. So here's a list of inputs and outputs, and let's plot these things. And the problem is that for an input of 3, in one case you got an output of 3, and in another case you got an output of 5. So it's kind of unpredictable. Like I put a 3 into the box, but how do I know if I'm going to get a 3 or a 5 out of the box? So this is not a function. An easy way to tell is to try to put a vertical line through a graph of the function or a plot of the function, and you'll see what happens here is the vertical line hits the function in more than one point, which means that you have multiple outputs for the same input. So this is an easy way to tell if something's not a function, is if a vertical line will cross the graph more than once. Let's look at a concrete example of a functional relationship from physics. So here's a really bad cartoon of the Earth-Moon system, and what makes it bad is the moon is, well, too close to the Earth for how big it is represented here. Here's a better cartoon of the Earth-Moon system with the Earth here and the moon way over there. This is a much better picture of what's actually kind of going on. Is it turns out when people go up to the space station, they're actually only like a few % farther from the center of the Earth than you are right now. So on a picture of the size of the Earth here, the space station's only, about that high or even lower than I'm showing it on this diagram here where this arrow is shaking. Well, it turns out where the space station orbits, it goes about 22.5 times the speed of sound on Earth. So it takes like an hour and a half for the space station to go around the Earth at this really high speed. Way out here where the moon is, the moon actually is moving pretty fast too, but it's about 3 times the speed of sound on Earth, but not nearly as fast as the space station goes, orbiting much, much closer to the Earth. Well, so the upshot is that when you make things farther away, they can, in a circular orbit, they would orbit slower, all right? Well, it turns out that the relationship between these things can be written like this. So if you put an input into this equation in units of how many Earth radii away you are, this equation will output how fast you have to go to orbit at that radius. So again, when you're close by, you have to orbit really fast, and when you're far away, you orbit pretty slowly. Well, so the idea here is you input a radius, an orbital radius, and you get one output for the orbital speed. Okay, so we say that the orbit speed is a function of distance away from the Earth. And so that function, as it turns out, actually looks like this. And so if you graph the function, you can see here close to the Earth where the space station is, you got to orbit at pretty close to this, Mach 23 or 22 times the speed of sound on Earth. And then as you go farther and farther from the Earth, so say here at 10 Earth radii away, you're orbiting somewhere around a little over Mach 7, or 7 times the speed of sound, I should say. And then as you go out here to where the moon is, 60 Earth radii, you're orbiting about 3 times the speed of sound on Earth. Well, so the upshot is for every one input of orbital distance, you get one output of orbital speed. So orbital speed is a function of r. For each input orbital radius, there's only one output speed. So this is a kind of a practical application of like what the idea is of a function. Well, I hope you enjoyed this and hope you find it helpful and interesting, and thanks for watching.